The Taylor series provides a means to predict a function's value at one point in terms of the function value and its derivative at another point. In fact, any smooth function can be approximated using a polynomial, as a polynomial using the Taylor series. A useful way to gain insight into how the Taylor series is beneficial towards numerical methods is to build it term by term. So therefore, if we have the first term of, that is f of x at I plus 1, approximately equaling the function value at f of xi, then in other words, the function values are the same, and this kind of makes sense if x of I plus 1 and xi are very, very, very close together. In other words, in a very small step size, it is likely that the function value at our next step is going to be the same at our current value. Now this approximation is fine if our function value is constant, but what if it changes? And I've drawn that in the figure below. If it changes, we can add additional terms to describe how it's changing. We could ask, is it increasing or decreasing? So we can add another term to the Taylor series, and that is the derivative, the first derivative at xi. So we say that if we had to sketch it, really what we're saying is that the value at f of xi plus 1, so that is f of xi plus 1, is really equal to the value at f of xi plus the derivative, which is the slope, multiplied by our step size, which is the difference between x of I plus 1 and xi. So we can draw that with an arrow. And we assume this would be for a linear change. So the function the change is linear. And we can add a second and third order term to increase the accuracy of our Taylor series. So the second and third derivative and so on and so forth. In fact, if we add all the terms, we can get an nth order approximation of our function. And we know, mathematically speaking, that the nth order Taylor series expansion is exact for an nth order polynomial. This is not always the case, and for sinusoids and exponential functions, a finite number of terms does not equal an exact approximation. In fact, each term adds more accuracy, but only ever so slightly. Now, as an engineer, you are the one who is going to have to decide how accurate you want your solution to be. So how do you quantify how accurate you want your solution to be? Well, you can base this on the remainder function. And here I've just written it as plus order h squared, but really what the remainder function can just be written that the remainder for an nth order Taylor series is equal to the n plus 1 derivative at some point epsilon multiplied by x minus this constant value, let's call it a, that raised to the power of n plus 1, or divided by n plus 1 factorial. Now we can define our accuracy based on our remainder term, but this remainder term has two drawbacks. The first is that our epsilon value is not known. In fact, it lies between the value of x at I and the value of x of I plus 1. But we don't really know its exact value. Secondly, in order to evaluate Rn, we need to know the n plus 1 derivative of our function. But now, what's the point of a Taylor series approximation if we know the derivative of our function? That would imply that we know the function and we don't actually need the Taylor series approximation. However, despite this, we do know what our step size is. That is x I plus 1 minus xi, which we can write as h. And we know how Rn in our error term scales with our step size. So if we have a zero-order Taylor series approximation and we halve our step size, we know that the error term is going to scale linearly with our step size. So in effect, we've reduced our error by half. So we can write this as R for a zero-order approximation is proportional to the step size. However, if we have a first-order approximation, so R1, the error term is proportional to the square of our step size. So if we halve our step size, we have in fact actually quartered our error value. So that is how we use the remainder term to try and approximate our errors, and we can look at this further with a few examples.